Lesson 6-1, Work and Power. Which of these following is not work? Pushing a stalled car, pulling a wagon, climbing stairs, falling down, carrying a heavy backpack down the hall. Would you be surprised to find out that it's carrying a heavy backpack down the hall? Let's discuss why. Work. Work depends on the force and the distance the force moves the object. We want the force in the direction of the distance. So work is the dot product of force with displacement. But the dot product is just the magnitude times cosine of the angle between them. So work is force times distance times cosine of the angle between the force and the distance. You can see here we've got the distance and the force. There's the angle. Our unit is a Newton meter, which is known as a joule. And work is a scalar, not a vector. There's no direction. Marcy pulls a backpack on wheels down the 100-meter hall. The 60 Newton force is applied at an angle of 30 degrees above the horizontal. How much work is done by Marcy? All right, so we have a 60 Newton force, and we're going 100 meters, and our angle is 30 degrees. So our work is FD cosine of 30 degrees. So it'd be 60 newtons times 100 meters times cosine of 30 degrees, which is 5196, or about, I guess we're in joules now, which is about 5,200 joules if we round. Drew is carrying books, 200 newtons worth, down the 100-meter hall. How much work is Drew doing on the books? Well, I don't know. Which direction is force? To hold the books, his force is up. To go down the hall, you were going that way. So our angle is, 90 degrees. So work is force times distance times cosine of the angle in between. So our work is 200 newtons, 100 meters, cosine of what? 90 degrees, which is 0 joules. Drew doesn't do any work carrying the books down the hall. Because the force is vertical, the displacement is horizontal. If your force and your distance are perpendicular, then there's no work done. You're carrying some books, 200 newtons, while walking down some stairs, the height of which are 2 meters and the length of which are 3. So 2 meters, 3 meters. Well, we could find an angle there because we're going to need an angle because our force on the books is up and our direction, our displacement's that way. So for our angle, I could say tangent of the angle is the opposite over the adjacent. Use inverse tangent and get 56.3 degrees. Also, to get the distance, I'll need to use the Pythagorean theorem, which is 3.61 meters. So my work is FD cosine theta. My force is 200 newtons. The D is 3.61 meters. Oh, what's my angle, though? It's not 56.3. It's actually this angle there. So that would be 180 minus the 56.3. So I get the angle between the force and the distance. So if I multiply that, I get negative 400 joules. Okay? Our work's negative 400 joules. Now, what if there is an easier way? That force times distance, that just needs to be the same direction. Since the force is just up and down, it's vertical. If I just look vertical, my force is 200 newtons. My displacement is down 2 meters. Oh, look, we get the same answer, much simpler. So we can simply, if we're given our force and displacement, and it's in joules, in the same direction, both vertical or both horizontal, then we can simply multiply those together. A suitcase is hanging straight down from your hand as you ride an escalator. Your hand exerts a force on the suitcase, and this force does work. Which one of the following is correct? The work is negative when you ride up and positive when you ride down. The work is positive when you ride up and negative when you ride down. The work is always positive. The work is always negative. So let's think about it this way. On the suitcase, the force is up. You're exerting an upward force. So when we're going up, so our displacement is up, those are both up, it would be positive. When we're going down, then I have a force up and a down negative. They're opposite directions. It would be negative. So the work is positive when you ride up and negative when you ride down. Two cars with the same mass do the same amount of work to get to 100 kilometers per hour, which is 60 miles an hour. Which is better, the car that takes 8 seconds or the car that takes 6.2 seconds, or maybe the car that takes 2.5 seconds? Well, y'all want the car that takes the shortest amount of time to accelerate. So, sometimes time is important when we talk about work. The rate that work is done is power. Power is the rate that work is done. So that means it is the work over the time. The unit for power would be a joule per second, which is a watt. A 100 kilogram car accelerates from 0 to 100 kilometers per hour in 3.2 seconds on a level road. Find the average power of the car. Well, what do we have? We have our mass is 1,000 kilograms. We've got an initial velocity of 0, have a final velocity of 100 kilometers per hour. Let's convert that. In 1 kilometer, there are 10 to the third meters. In 1 hour, there's 3,600 seconds. That gives us 27.8 meters per second for a final velocity. We have time as 3.2 seconds. But how does that help? We want to find power. Power is our work over time. But work is force times displacement, and our force and our displacement are the same direction. They're both forward. So the cosine 0, which is just 1. But force is mass times acceleration, and cosine of 0 is 1. We also had that v squared equals v0 squared plus 2a d minus d0. Let's say we start at 0, so it's just 2ad. If I subtract the v0, and divide by 2. Or we could say this is 1/2 v squared minus 1/2 v0 squared. I could plug that in for the AD. Which if we distribute be 1/2 mv squared minus 1/2 mv0 squared. Wait, we already saw that as kinetic energy. So it's a change in kinetic energy. All right. So our mass was 1,000 kilograms, and our final velocity was 27.8 meters per second. Mass is 1,000 kilograms, but our initial velocity was 0, and our time was 3.2 seconds. If I put all that in my calculator, don't forget to square, I get 121 approximately 121,000 watts, otherwise known as 121 kilowatts. You think, oh wow, well, that's only about 162 horsepower. Electrical energy is often measured in kilowatt hours, because if power is work over time, then power times time is work. If it costs 10 cents per kilowatt hour, how much will it cost to run a 1,000-watt microwave for 2 minutes? Well, if our power times time is our work, our power is 1,000 watts, but I would like it in kilowatts. So 1,000 watts is 1 kilowatt. And our time is 2 minutes, but I don't want 2 minutes. I would like it in hours. There are 60 minutes in 1 hour. So it's 1 over 30 hours. So our work is 0.0333 kilowatt hours. Now if I times that by my 10 cents, we get 0.003 dollars.